Hey everyone, and welcome to this explainer from the Foundry by Forge College. I'm absolutely thrilled you're tuning in today because we're looking into the really intricate, high-stakes world of transaction forwarding. If you've ever found yourself wondering how a high-performance blockchain like Solana actually processes thousands of transactions seemingly all at once without completely melting down, well, you're in exactly the right place. We're going to unpack the complex logistics of forwarding algorithms and priority handling, keeping a tight focus on the engineering side of things. It's fascinating stuff, so grab your notes and let's get started.
Okay, so here is our agenda for today, basically our blueprint for how a high-speed sorting facility works on the blockchain. We'll kick things off with the forwarding bottleneck, move into the core forwarding algorithms, talk about setting priority rules, examine the constraints and trade-offs, and finally look at engineering the hybrid solution.
All right, let's jump right into part one, the forwarding bottleneck and the underlying logistics of validation. So every network engineer eventually runs into this fundamental logistical problem. It's just the harsh reality that validators face every single day. You have extremely limited bandwidth between nodes, incredibly short time windows, and this overwhelmingly high volume of transactions just pouring in. I want you to imagine a massive, chaotic traffic jam at a futuristic toll plaza. That is essentially what your validator is staring down. You've got an aggregated buffer of, say, 10,000 pending transactions, but you only have 2,000 slots of forwarding capacity to reach the next upcoming leader within their really brief acceptance window. I mean, how do you fit 10,000 cars into 2,000 lanes? You desperately need some kind of intelligent sorting mechanism. To see how we tackle this, let's build a bit on our previous lessons. Remember how the old persistent mempool model worked? It was essentially just a giant waiting room where transactions sat locally until a miner finally asked for them. But Solana's Gulfstream forwarding model? It's proactive. It aggressively ships transactions to upcoming leaders before they even take the reins. Now, this mempool list approach is undeniably fast, but it means you're forced to make sorting and routing decisions proactively under immense pressure. And that brings us perfectly to Section 2, Core Forwarding Algorithms, or what I like to call the mechanical sorters. If we treat our network like a high-speed sorting facility, we need mechanical sorters. These are the deterministic and probabilistic rules dictating exactly who gets through that bottleneck and when. The absolute simplest one we have is FIFO, or first in, first out. You can picture this as your classic, reliable conveyor belt. It forwards transactions purely based on the exact order they arrived. It's incredibly easy to implement, and it's wonderfully fair from a chronological standpoint. But the problem? Well, it's completely blind to economic signals. And honestly, that's fine, until you have a highly sensitive, premium smart contract transaction waiting endlessly in line behind 5,000 people casually buying digital coffee. So to solve that digital coffee problem, we introduce strict priority queuing. Think of this one as the VIP fast pass lane. Here, you forward transactions sorted strictly by a single metric, which is usually whoever is paying the highest fee per signature. This is great because it absolutely minimizes latency for your top scored items. But as you can probably guess, it introduces a massive risk. If that VIP lane is always full, your lower priority transactions are going to get completely starved out. They literally might never make it through the toll plaza. Next up, we have weighted fair queuing, or WFQ. Imagine introducing a meticulous traffic cop to our toll plaza. Instead of just having one VIP lane and one slow lane, WFQ allocates forwarding bandwidth proportionally across different classes of traffic. So you might have one class for payments, another class for smart contracts, and a class for system instructions. This is brilliant because it ensures that critical, latency-insensitive background traffic still gets a minimum guaranteed throughput while simultaneously preserving fast lanes for your premium classes. Finally, we have speculative batching. You see, sometimes scoring individual transactions just takes way too much computational overhead. With speculative batching, you essentially throw a massive bundle of transactions onto a freight train that's aimed at a specific upcoming leader window. You aren't sitting there scoring individual items, you're just trying to maximize total throughput under the uncertainty of leader timing and shifting network dynamics. When we map all these out side by side, you can clearly see the real trade-offs in protocol design. Just take a look at how implementation complexity and state overhead rise drastically as you move away from the simple conveyor belt of FIFO all the way up to the meticulous, class-based scheduling of WFQ. The takeaway here is that you can optimize for order, you can optimize for fees, or you can optimize for proportional fairness, but you are always going to pay a price in complexity. Let's move on to Section 3,
setting priority rules, and how we actually go about scoring transactions. Before we can even use our mechanical sorters, our decision layer has to tag and evaluate the transactions themselves. If we aren't just using a simple FIFO setup, how do we actually assign those priority scores? Well, the two heavyweights in priority rules are fee-based priority and age-based priority. Fee-based sorting utilizes a really measurable economic signal. It beautifully aligns incentives. If a user wants their transaction processed faster, they just pay a higher fee. Pretty straightforward. But on the flip side, age-based sorting relies on the first seen principle. It guarantees temporal fairness and chronological correctness, which is absolutely vital for certain decentralized applications where the exact transaction order dictates the logical outcome. Which brings us to Section 4, constraints and trade-offs, and the systemic side effects that come with them. Applying these priority rules in a real-world, highly constrained environment is where things get really fun for network engineers, largely because it introduces some pretty dangerous side effects. If you rely purely on one rule, total chaos ensues. A pure fee-based system, for example, can cause fee oscillation, where relayers are constantly chasing these transient fee spikes. It also causes herding, where all the validators flood the exact same high-fee transactions to multiple leaders redundantly. And pure age-based systems, they are incredibly vulnerable to flooding attacks, where bad actors can just inject thousands of cheap transactions specifically to clog up your queues. By the way, studying these exact systemic network dynamics is a core part of the broader courses we offer at Forge College, because misunderstanding these trade-offs can literally bring a live network to its knees. So let's head into our final section, Section 5, engineering the hybrid solution to balance the system. So how do we avoid crashing the network? Well, we have to carefully engineer a balanced machine. We know the algorithms, we know the rules, and we definitely know the side effects. The ultimate blueprint for success requires blending these concepts together. Let's walk through a real-world load scenario. Imagine you get a sudden influx of 5,000 low-fee payment transactions, immediately followed by 1,000 high-fee smart contract calls. If your forwarder uses pure fee priority, those 1,000 smart contracts are going to jump the line and the payments get endlessly delayed. Your queue growth is just going to explode. But if you implement a hybrid system, you clear those high-fee contracts immediately while still distributing enough capacity to keep the regular payment queue moving along. To execute this successfully in practice, engineers use a hybrid quota system. You carve out a specific slice of your bandwidth, let's say 30%, and reserve it exclusively for strict priority, capturing those high-fee VIPs. Then you safely distribute the remaining 70% using weighted fair queuing. This approach protects your system-critical transactions, it guarantees fairness for everyday users, and it still manages to provide a predictably low-latency lane for your premium traffic. It's the best of all worlds. So the absolutely crucial point here is that a perfectly engineered forwarding system has to balance measurable objectives against the harsh physical realities of the protocol. You must prioritize your metrics. Are you optimizing for median latency, or are you worried about worst-case P99 latency? You have to protect fairness using quotas or admission controls. And you must always account for your ultimate constraints, your bandwidth caps and those fleeting leader windows. All right, so you now understand the blueprint of forwarding algorithms. But honestly, that leaves us with one incredibly provocative question. You know the algorithms, but how do you actually tune those weights and quotas live while the network is under massive pressure? Well, that is exactly what you need to master next. To dive into latency reduction, dynamic tuning, and to explore a massive library of other Web3 subjects within our advanced Solana concepts track, I highly encourage you to visit forge.college. Go check out the resources, keep building that expertise, and I will see you in the next explainer.